Welcome, everybody. Welcome to the Bene Studio workshop. And my name is Bene. I'm the CEO of Bene Studio. And at Bene Studio, we do software design and development, and we are committed to cutting-edge technologies and solutions in mobile, in web, and in backend development as well, also in IoT integrations and AI integrations. Today we will work on a project which is a small application, and building this application you can learn a lot about state machines. And within one of our projects, David faced a few issues related to state machines, so he dig deeper into the topic and came up with nice solutions. And as our motto is, we love sharing knowledge. We would like to share this knowledge today with you. So please welcome David, our speaker, and also raise your hands, or if you are joined virtually, write into the chat, because Tamás will help you. Tamás, can you show yourself? Yeah, Tamás is here, and he's always here to help you, so raise your hand and ask. And I would like to say thank you to the organizer team behind this event, Fatima, Vicky, Alice, and also to our partners, Budapest GS Meetup Group, and to a conference, JS Nation. And after the workshop, you can win a free ticket to the conference, so don't go anywhere. We will have an exciting throw even at the end of the event. And now let's start the workshop and build a nice application with David.
Did everybody get the repository cloned? Okay, cool. We won't need any special tuning today. So this little example is designed to work with a simple browser and with a text editor. And let's talk about what we will build today. We will have a very simple application where we will display a game character and move between its possible states. And we will use and actually implement a small state machine library that will encapsulate this logic, which states are possible to reach from which one, but we will see it in a moment. But first, let's get some background. Imagine an application. You don't need to read the little text on the graphs. It's just an illustration. So imagine an application that has a user flow with over 20 pages, more than 10 conditions that can dictate how you move between these states. The flow even dependent from input values. So you could imagine, for example, an authentication flow where the registration is integrated. You can use one-time passwords. Maybe your phone number is expired, and all of these can influence how you move through these different pages. Or you could imagine medical survey, where previous conditions change the forms you will need to show later on. And as you imagine, especially for medical applications, accuracy is very critical. And as always, requirements change frequently. So you need to isolate this logic and make it maintainable. You don't want to scatter it around in your application. And state machines are a great fit for this problem. So actually we are using something like this in our mobile application, where we built a central service that dictates how the user moves through the different forms. So a state machine has finite number of states. We need to define in advance what states are possible, have finite number of elements that can move the application from one state to another, and has an initial state and the transition function that will decide how to move between these. Also, it can have a possible set of finite states. For example, if we finish the flow, we will log the user in. But if we only work with these, it has limitations. So to overcome the limitations what simple state machines have, David Harrell introduced in its 1987 paper state charts that add extra features to state machines. It's not just a visualization, but these are also executable. And for example, one extension is compound states. So this is an example from our application. We have standing, walking, and running state. And we move to the walking state with the arouse. And with shift, we move to running. But as we add more and more states, if we want to exit both walking and running with the left key, then we need to add extra transitions. But if we can group these states together to a compound state, we will call it move in our case, then we can define an initial state inside that compound state and point transitions to the compound state, and thus reducing the number of transitions we need to maintain. One other extension is parallel states. So if we have two variables, for example, the number of transitions and possible states will explode as we add more and more separate fields. So we can model these with parallel states, again, reducing the complexity of the graph and basically the code. And it's nice and good if we have a state machine that works, but we need to control the outside world, and we can use effects for these. For example, a state can have entry and exit effects that executes side effects, like in this example, turning on an alpha light, but it can be an HTTP request storing to the local storage or anything like that. And one very good example of state charts is xstate. It's a practical, well-documented JavaScript library. It introduces much more than we will build today. Our example will be a simple copy of xstate, let's say that. It even has guards that can prevent transitions from happening. It has context that's basically mutable state that the chart can use in different places, and much more. It also has a visualizer. It validates if what you configured is correct or not, and also executable. And I will have a reference up with some GitHub repos. For example, Amplify UI, it's an AWS service, uses xstate for its whole authentication flow. So let's take a look at our example. These are the states we will have. Our character will be able to stand, jump, attack, squat, walk and run. And you can see that we need to take into account where we are currently. So not all states are reachable from any other state. And we will have some timers as well. For example, we will move back from the attack state with a timer when the animation finished, and the same with jumping. Okay, so I think we can jump into coding. We have some assets because we do health stack. Our character will be a doctor, and its attack phase will be using hand sanitizers. I chose a very simple solution for rendering because I didn't want to deal with canvases and game loops today. We will just basically insert HTML into this page, and we can focus on the coding part. We have 3 files, game.js that will house our game-specific logic. We have machine.js. This will house the little statechart library. And we will have a UI class that will render the states and listen to keyboard events. So let's get started. We will just insert some HTML, so we need to get references with document get element by ID. So we have character, property. We can use document that get element by ID and character. And we will have a render method. And here we will just set the inner HTML of the character with a string literal. And conveniently, we have the same names for the states as the assets. So we don't need to do any mapping. And the render function is to accept the state what we want to render. And one trick is after a question mark, we will add the current date time, and this will force the browser to re-render. We also need to listen to keyboard events. So document that at keyboard event key down, and we have to create a method for this. Let's call it handle keyboard event. It accepts the event. And just logs it out for now. And we can add this here. And we need to bind the this context, so otherwise it won't have access to it. Let's create a new instance of the UI. And render the stand state. And I forget the closing tag here. We can open it in the browser. And I think I messed up the styling. So we just need to change this one. So open style.css and set 70 view height. It's styles.css at the image tag. And much better. We have the nice animated GIF. And if we press the arrows, we can show the events. Can you raise a hand if you got this working? Can you raise a hand if you need any help?
Do you have Wi-Fi? Sorry.
Sure. It's this one. If it doesn't refresh, you might need to select the network tag and select disable cache.
I actually have a question. I still don't get why do we add the date?
Because the browser will cache the GIF and wants to run it again once you run it. And we have animation that doesn't go in a loop, but just lasts for 2 seconds. And if you don't add the date, it will just run once, and when you insert it again, it will use the cache. If you have questions, you can raise your hand, and Tamás will help, or me. But if no questions, then okay. We will need a way to notify different parts of the application, and we will use a simple listener callback for that. So we create an on keyboard event method that accepts a callback, and we will store this callback in a listener. And in the handle keyboard event function, we can call this listener, and we can pass in the key. And again, we will use the same names for the transitions as the name of the key. This way, we don't need to do any mapping. And we can delete this part. We can move to the game.js. And we would like a configuration. So let's create a config object. And it will look something like this. We have states. And we have a state for standing. And these are all fields in the object. And we will have one for squatting. And we will use lookup by key to find these states. And we will define transitions from these states, how to move to different states. And this will be also a field. And with arrow down, we will move to squatting. And from squatting, with arrow up, we will move to standing. And we will also need an initial state. And it will be standing in our case. Let's take a look at the library that will understand this. Let's move to the machine.js. This will accept in the constructor the config. And it will set the state to the initial state. We have a transition method that will accept the name of the transition and will move the machine to the next state if we can use the transition in the current state. First, we need a reference to our current state, and we can do that by a lookup. This will be response state, so it will look it up by name. And we will accept the transition name here. And we just open this on the side. It will use lookup again to find this property. And if we can find it, that means we can move to the next state. And the next state will be the value here. So the next state will be current that transitions and look up with the transition name. And if we have next state, then we can set this state to this next state. So let's use this in our game.js. So in the constructor, we will need a new instance of the UI. And we will need a new instance of the machine. And we pass the config inside it. We will need to handle keyboard events here as well. So let's create a handle keyboard event method where we accept the event and we send this to the machine. And after we accept the event, we will render it with the UI class, this.ui.render this.machine.state. And it will be the updated state. And we can register this handle function with this.ui.onKeyboard event. Yes, we need to bind this again. And we will need to render it in the constructor as well, otherwise we won't see it in the beginning. And it's states and not state. And yes, we should see it standing and squatting.
If you press again after the level does the toggle down, it restarts.
Yeah. Does anybody need some help? Okay. Let's add the attack state. From transitions with from the standing state with space, you can use the square brackets to index the key like this. We will get to attack. And if we opened up right now. You see that this has a fixed length of animation. So we will need a timer that will bring us back to the standing state. First, I will just create the object we want to see, and then we will implement how to use it. So this will be a raw function that returns an object, and it will have a property of attack timer with capital letters. And this will be one of our effects. And this itself will be an arrow function, and this will be executed when we enter the state. And here we start a set timeout with 1 second, because that's how long the animation takes. And after this set timeout, we need to move back our machine to the standing state. And this function will accept a transition function, which will be a reference to our transition function in the machine.js. And we will use this transition function to dispatch attack timeout. And this will bring us back to the standing state. So in the attack, we will have a new field called entry. And this will be the entry effect. And it will start the attack timer. And we will have a transitions object like before. And here we have attack timeout, and it will bring back to stand. If we go back to the machine class, we can add the function that will register these effects. So it accepts the effect creator function. And we will assign it to the effects property. We call the effects creator and bind and pass in the transition function, so we can use it inside the effects. And if we go back to the game class, in the constructor, we need to register these effects. So on machine, we can call add effects and pass in the effect creator by reference. But we have a problem because we render on every keyboard press, And now our state will change internally. So the machine needs to be able to notify the game that something changed. So we can delete this render from here, and we need to go back to the machine and add an onChange method. This will use the same pattern. It will accept the callback. And assign it to the listener field. And in the transition method, after we assign the new state, we will notify the listener. And we will pass in this the state. And we haven't run our effects yet. So we need a new function for that. It will be run effects. It will accept the node, the state node, that will have the effects property. So we can retrieve the effect name from there. And we can look up that effect by name. And execute it. And we will need a reference for the next node. So let's change this to next name. Because we store the state as a simple string.
Can you get a little bit slowed down because it's hard to follow?
Sure. But if you have any specific question, we can help direct you as well.
No, it's too fast.
Okay. So we need the reference to the next state node, so we can run the effects on it. And we can just select it by name, and then we can use this .run effect with this state node. And let's see if this works. No, because we didn't register the onChange listener. So if you go back to the game.js, we need a handle state change method where we accept the new state and then render the UI with this new state. And we also need to register this as well with the machine's onChange notifier. No, this will be handle state change, and we need to bind this as well. And now it should transition back to the standing state. Then let's create a new state. We will call it move. And this will be a compound state, so it will have states itself. And we will use the same format as before. We will have walking and running. And it will have an initial state of walk. These will have transitions too. From walking with arrow left, we go back to standing. And with the shift key, we go to running. And it's almost the same with running, just we cycle back and forth with walking and running, because we only listen for key down events for now. And from standing, if we press arrow right, we go to this move state. What this means, in the machine.js, we no longer can use simple key lookups because these tests might be nested inside each other. So we will need to go through the tree and find this node. We could use some sort of caching, but we're not going to do that today. We will traverse the tree every time. So let's create a getNode method that accepts the name and the states and loops through them with object of entities. So we will say const array key node of object that entities and the states. So this will loop through every property of the object. And if we find a key with the name we are looking for, then we will return that node. Otherwise, we need to go deeper in the tree. If this is a combined state, of course, otherwise we can't go deeper. We just go to the next field. We call this function recursively again, and this will be our result. So const res again equals this that get node. We pass down the same name we are looking for, just with the states of that node, so of the compound node.
Node wants states, isn't it? Or just state wants them?
Good catch. And if we found it, then we return it.
And in the if condition, it's state or state.
Good catch again. And in the transition function, we need to call this that get node. This that state will be the name of the current state, and this that config that states will be the states we are going to go through. And we need to change it here as well, because to run the effects we need to find nested nodes too. So next state will be this dot get node, next name, and this dot config dot states. See if this works. Oh, no. Because we not only need to select this one, but select its initial state, because this can be a target state. But so it can be a target state, but the new state will be its initial state. So if this points to a compound state, we will need to select its initial state. But these can be nested as well, so we need to write a new function for this. So if we go back to the machine.js, we need a new function called get next state, and this will take into account the initial states. This will accept a name. This is the name of the state we are targeting. We will get a reference to this node with the previous written get node function. We pass down the name and the states. If this node has initial state, then it means it's a compound state, and we need to check its children. So we will call this function again. Just with the initial state of this compound node and the node states. So this is another traverser where we go down into the tree, where we find an endpoint that is not a nested state. And here we will return the name and also the node. Because if we, for example, target the move state, the new name won't be move, it will be the initial state of walking. Okay. And we will need to use this function to get the next state in the transition function. We pass in the next name and all the states. And this will return an object. So we can check if next state has a name. And here we no longer need this one, because it will receive the node itself, the node 2. And we can use xstate that name. Okay, let's see if this works. Yes. And I think it's a good time for a break. And
You got 2 return statements without semicolons after the ASI is not going to work. If you,
could you repeat?
in get next state, you put them, you see your return statements not having semicolons and not be freaking out the parser.
Oh, the semicolons?
Yeah, after returns, sometimes weird things happen if it doesn't have it.
Okay. So let's have a break, and in the break too, if you have any questions, I'm available. With the original graph, we had the ability to target this compound state in both directions, but we can only target it in one currently. So if we target it with a transition, then it will select the initial state, but if we want to move out from it, we won't be able to. Because if we are in one of the child states, we only listen to the transitions that that child state can understand. So if we are in the walking, we can only understand these. But if we want to do something like this, that the move compound state will have transition themselves, that means if we are inside here, we also want to see if one of its parents can understand that transition. So we can delete a row left from these places, and we will make it work that we can exit this parent. So one way to do this is to go to the tree and store the path of every node, and then once we are in a nested node, we can go through the parents and see if any of them understands this transition. Create a traverse method for this one. This will walk through the tree and add a path variable to every node. It will accept states and path. And as previously, we will loop through with object.entities. So const array key value, or we could call it node here as well, of object.entities states. And we create a variable with the current path here. I spread the previous path and add the key, the name of the state. And we assign the current path to that node in memory. And if the node has states, we continue the traversal. I will pause here. And in the constructor, we will do this traversal once. This.traverse, this.config, that states. And we can log out the config here, so we can see if we did it correctly. And if we go here, for example, in the run, we will see that's inside move, and we are the run state. But in the transition function, accessing the transition like this won't hold true anymore. And we need a new method called getTransition. Where we accept the current node and the name of the transition. And before we did the traversal out of time, we can just simply loop over this one. So we can loop over current.path. And it will loop over every parent node. We can use the getNode method to pass in the key that we are currently looping over. And this that config the states. So we have a reference to that node. And we need to check if that node understands that transition, and it can produce a next name. So we say no that transitions and the name. It might be a bit confusing. This is transition name. So this, because we have the name of the state and the name of the transition. And if we found the next name, then we can return it. And in the transition function, we can call this dot get transition. And we can pass in transition name and the current node. Here you can see everything we did now. And now it should work. Yes, so we no longer need to target directly. Liz, how much time we have left?
Around half an hour.
Okay. Yes?
What we did with taking this traverse, what is this doing? Because we can't see the difference. Yeah.
We did that. We don't need to target from the walking state the standing state, but we can target it from the move compound state.
They are not making a decision.
So the application works the same, we just spared some extra transitions. We don't need to define.
Can you show me the machine class constructs?
Sure. Sure. Okay, then we can add some extra features just by using what we already have. So let's say after running, our character will be tired. So let's add an entry condition for the running state, call it run timer, and let's add a transition that we name run timeout, and it will bring it back to walking. And we can copy this other effect and just make some modifications. Just call it run timer and run timeout. And let's say it's just 500 milliseconds. And it will go back. And without any code modification, we could add extra features like this one. The problem comes when we press this a lot of times, and we start a new timer every time, and we don't cancel them, because here we have another way to move out of the state other than the timer. So we can implement a cleanup for these timers. So let's say this effect function will return a cleanup function, and we save the ID of the timeout, and here we call clear timeout and pass in the ID. It is not a problem with the attack, because we only move from the attack state once once the timer finishes. But we could do a timeout there as well. If we go back to the machine class, when we run an effect, we can save the cleanup function. I will move it to a new variable, so it's a bit cleaner. And before we run any effect, we run the previous cleanup. And with this, we will always have correctly working timers. I think we are still missing a jumping state. But this is just a matter of configuration. If we go back to the game.js, we can add a new class called jump. It will have a entry effect, because this is a fixed length animation as well. We will call it jump timer, and we will have one transition jump timeout, and it will bring us back to standing. And we also need to add a row up to the standing state transitions to move it to jump. And we need to add a new effect for this one. Call it jump timer, jump timeout. And this animation takes 2 seconds, so we need to wait 2 seconds before we transition back to standing. And this completes every state we wanted to cover. So thanks for joining, and I will be available after the workshop to ask any questions.
Let's conclude this workshop, at least this part of the workshop. First of all, thanks David for this great material, and thank you everybody to join us today. And I ask you, raise your hand who managed to put together more or less this application. Wow, great success. It's cool. Yeah, and after the formal part of this workshop, we will have some beer and pizza. We will play darts as well. And David and Tamás are open to answer your questions. So if you have a few in your mind, or you haven't finished the application, then it's time to have some guidance. And after that, just enjoy the company and have some fun together. And today we would like to find the winner for the conference, JS Nation. So for that, let me ask a kind guest of us. Yeah. Okay, so it's official. Yeah, please, yeah, mix it, and from the deep underneath. Yeah, no cheating.
I want my name. So the winner is me, actually. Magic hands.
Yeah.
Yeah, I don't know.
You have magic hands. Congratulations. Yeah, congratulations.
Okay.
It's official. Yeah, enjoy the conference. And yeah, and
Okay.
yeah, you have lucky hands.
Yeah, I do.
Yeah, it must be used for coding as well.
Yeah, right now they don't want to fire me, so I guess.
Okay, great. So congratulations again, and guys, we have pizza, beer. So thank you very much, and congratulations, David, Tamás, and Joseph.